Okay, some additional problems for Chapter 7. So here I have a railroad car. It's going to have a mass of A, and it's going to be traveling at a velocity of A, and a load is going to be dumped into it. That load is going to have a mass of B, and it's going to have a velocity of B, which is going to be 0. It's not moving. So this is kind of the before scenario. Now, afterwards, we're going to have the masses are going to add together. We're going to have mass of A plus mass of B inside of the cart, and it's going to be traveling at some new velocity. I call that V prime. That's the same for both of these guys. Now, this isn't perfectly inelastic collision. They stick together. So we know that kinetic energy is not conserved. It's never conserved when they stick together like this. What is conserved, however, is momentum. We can always write the momentum beforehand is going to be equal to the momentum afterwards. What is the momentum beforehand? Well, that's going to be the sum of the momentum of the individual parts. So mass of A, velocity of A, plus the mass of B multiplied by the velocity of B. All that's going to be equal to the momentum afterwards. And in this case, they're sticking together, so I add the masses together, mass of A plus mass of B, multiplied by their new velocity. Now, I know velocity of B was initially not moving, and I simply solve this guy for V prime, which is the velocity I'm interested in, by dividing both sides by the sum of the masses, as such. Now I simply plug everything in. So 7150 is going to be the mass of A, my cart right there, and it was initially traveling at 15 meters per second. And I'm going to sum the masses down here at the bottom. 7150 was the mass of A. The load that I put into it was 3350, and you can see it's going to lower that velocity. The velocity at the end of the day is going to be 10.2 meters per second. Okay, problem number 18 is asking about impulse. We know that impulse is going to be equal to a change in momentum, so mass velocity final minus mass velocity initial. It tells us that it comes in with an angle of 45, and it's going to show it leaving with an angle of 45 and the same speed. What that incidentally means, this is going to be an elastic collision. Energy is going to be conserved because it is the same speed. What that tells us, though, is both of these are 45 degrees. Tells us that the velocity final in the y is going to be equal to the initial velocity in the y. It's not going to change velocity in the y direction. Velocity final in the x, however, is going to be in the opposite direction as velocity initial in the x. And we can relate velocity initial in the x to the initial velocity, simply going to be the velocity multiplied by the sine of 45. So the change in momentum in the y direction is going to be essentially 0. It's not going to change the velocity. The change in momentum in the x direction is going to be mass velocity final x minus mass velocity initial x, which is going to be equal to negative mass velocity initial x minus mass initial x. Here I have simply gone ahead and used this relationship right there. So that's going to be negative 2 mass velocity initial x, which is going to be negative 2 mass velocity sine of 45 degrees. Go ahead and I plug all these guys in here. I know that the negative 2 multiplied by the mass, 0.06 kilograms, multiplied by the velocity, 28, sine of 45 degrees. And I'm going to end up with negative 2.4 kilograms meters per second. Now what the negative means is it tells us something about the direction. It tells us that it's going to be to the left in the negative x direction. Okay, another problem with momentum and impulse. So I'm going to have a fullback, and he's going to be traveling with some velocity. So this is going to kind of be a beforehand. And then afterwards, he's going to be tackled by this big dude and mass by fullback. And these guys are going to have a final velocity equal to 0. It's going to kind of be my after picture. I'm asked for the momentum of the fullback, where momentum is simply equal to mass multiplied by velocity. And what I'll do here is I'll say he's traveling to the east, so this is going to be east, and I'm going to call east positive. If I get a negative number, that simply means to the west. So his mass is going to be 95 kilograms, and his velocity is going to be 3 meters per second. So I'm left with 285 kilograms meters per second. This is going to be positive, so that means he's going to the east. For part B, I'm asked what the change in momentum is for this guy, and that's going to be the momentum final minus the momentum initial. The final momentum is going to be a big fat 0, and his initial momentum is going to be 285 kilograms meters per second. So the impulse acted on him is going to be negative 285 kilograms meters per second. The negative means the impulse was to the west. For the tackler, the impulse is going to be also 285 kilograms meters per second. However, it's going to be in the positive direction or towards the east. You can think of this in terms of Newton's third law, where that is an action-reaction pair. And lastly, I'm asked for D, the average force. We know that the average force is going to be the change in momentum divided by the change in time. So this is going to be 285 kilograms meters per second, and this collision happened over 0.85 seconds. So it's going to be 340 newtons, and this is also going to be towards the east because it's asked about the tackler, therefore I used my positive momentum. Okay, problem number 27 is an example of an elastic collision. Remember, with an elastic collision, energy is going to be conserved and momentum is going to be conserved. And it turns out that we need this. This is going to give us two separate equations. The reason why we need two equations is because we're going to have two unknowns. We're going to have the velocity of A afterwards and the velocity of B afterwards. The only way to solve for two unknowns is to have two equations. Now, I'm not going to rehash the example in the book where we derive equation 7.7 using energy conservation that relates the difference in the velocities beforehand to be negative the difference in the velocities afterwards. However, that's going to be a B prime. However, I will once again say that this equation right here is only going to apply to elastic collisions. You cannot use this for inelastic collisions. And I'll put an exclamation point, because that is a very important concept. What this allows us to do is say, well, I know what the difference is beforehand. That's going to be 5.5 meters per second minus 3 meters per second. That's going to be negative velocity A prime plus velocity B prime. Is I can go ahead and I can write this one of the velocities afterwards as the other one. So I'm left with 2.5, and what I'll do is I'll add velocity A to both sides, and now I have an expression for the velocity of B afterwards. I can use that, and I can say, well, I know that momentum is also going to be conserved, so the momentum beforehand is going to be equal to the momentum afterwards. So mass of A, velocity A, plus mass of B, velocity of B, is going to be equal to mass of A, velocity of A afterwards, plus mass of B, velocity of B afterwards. I can take this expression for velocity of B and put that in right here. So I'm going to get mass of A, velocity of A, plus mass of B, velocity of B. It's going to be equal to the mass of A, final velocity of A, plus mass of B, and now it's going to be 2.5 plus the velocity of A afterwards. This is going to let me rewrite this guy. I'm going to say now I'm going to have 2.5 times the mass of B plus mass of B, final velocity of A, and I can factor out a final velocity of A kind of as such. I can say that's going to be the mass of A plus the mass of B, and of course I still have my 2.5 multiplied by the mass of B. I can subtract this from both sides, and I can divide both sides by this, and what I get is the velocity of A is going to be equal to the mass of A, velocity of A, plus mass of B, velocity of B. Both these are the beforehand velocities, minus 2.5 mass of B, and divide that by the sum of the masses, mass of A plus the mass of B. And now it's a simple matter of plugging these in, where A is going to be the tennis ball, so 0.06 kilograms traveling at 5.5 meters per second. I'm going to have my other ball, 0.09, and this is going to be, I can essentially subtract the velocities, so that's going to be 3 minus 2.5. I've just done a little bit of factoring there on you. And that's going to be 0.06 plus 0.09. So I can get the velocity of A afterwards to be equal to 2.5 meters per second. I know that if I add 2.5 to the velocity of A, then I get the velocity of B afterwards. So I get the velocity of B is going to be 5 meters per second afterwards. Lastly, a sample center of mass calculation. Here I'm going to have a CO molecule, so it's going to be a carbon and an oxygen, and I know what the distance in between them are. And I'm asked how far away the carbon is from the center of mass of the molecule. I know what the relative masses are in terms of atomic mass units. So the easiest way to do that is to say, well, I'm going to set up my origin such that my y is going to be here, my x is going to be here, and I'm simply calculating out what this distance is going to be, picking the carbon to be my 0 point. So the distance to the center of mass is simply going to be the mass of the carbon, the distance of the carbon to the where I choose my origin to be, so you can see that's going to be 0, the mass of the oxygen multiplied by the distance to the oxygen molecule, divided by the sum of the masses of these two molecules. So you can see that I'm going to have my mass is going to be 12 units, my distance to the origin is going to be 0. I'm going to have a mass of 16 units, and the distance is going to be 1.13 times 10 to the negative 10th meters. And I'm going to have 12u plus 16u. You can kind of see that these u's are all going to go away. And I'm going to end up with a distance between the carbon and the center of mass to be 6.5 times 10 to the negative 11th meters. Now that's larger than the distance in between them, so that if this is the middle of the distance in between them, the center of mass is going to be closer to the oxygen. That makes sense. Oxygen has more mass than carbon has.